And here's another example of how we can calculate the electric field by using Gauss's law. In this example, we'll calculate the electric field created by a uniformly charged sphere. We will use the result from the video where we calculated the electric field created by a point charge. So if you haven't seen that video, please go back and watch that video first and then come to this video later. So we'll start with a sphere with the charge plus q spread uniformly throughout the entire volume of the sphere. The actual physical radius of the sphere will be big R, and we will ask what is the electric field at a distance little r away from the center. Now we have two situations here, possibilities. One, if little r is actually larger than the actual physical radius of the sphere, that means we are outside the sphere. We have the same spherical symmetry as we discussed in the example when we calculated electric field by a point charge. So the electric field vector will be pointing outward in a radial direction. Here's our Gaussian sphere with area vector equal to dA, again parallel to the electric field. Applying Gauss's law for this Gaussian surface that is outside the actual physical sphere, we have the electric flux here being simply the integral of E dA must be equal to the enclosed charge over epsilon naught. Here epsilon naught is the permittivity of free space. Since we're outside the actual physically charged sphere, we have enclosed the entire charge plus q. So following the steps as in the previous video for the electric field of a point charge, we arrive for the expression of the electric field as 1 over 4 pi epsilon naught times q, the enclosed charge over r squared. Please note that this result is identical to the result for the electric field produced by a point charge. So the lesson out of this activity is that as long as you're outside the sphere, it doesn't matter if it's a point charge at the center or there's some extended sphere with a radius r. Things look a little bit different, however, when we go inside and ask the question, what will be the electric field if little r is actually less than the big R? In other words, what happens if we're inside the sphere at the distance r? What will be the electric field? Well, we'll repeat the steps again, only now our Gaussian sphere will have a radius smaller than the physical radius big R, so we're inside the sphere. But otherwise the steps are the same. We will have that the electric field will be equal to 1 over 4 pi epsilon naught times the charge enclosed over r squared. Here again, r is the little r, which is the variable that gives the distance to the location where we're solving for the electric field. The difference here from the previous situation where we were outside is that once we are inside the actual physically charged sphere, we're not enclosing the entire charge. So q enclosed here is not plus q, and we need to find out what that value is. For that, we will use the fact that the charge is uniformly distributed throughout the entire sphere. In other words, the ratio between the enclosed charge and the entire charge is the same as the enclosed volume versus the entire volume. Geometrically, this will be written as the enclosed charge will be equal to the total charge divided by the entire volume of a sphere, which is 4 pi over 3 times the radius of the charged sphere, so that's big R cubed, multiplied by the volume, the enclosed volume, which is 4 pi over 3 times the little radius cubed. After canceling the 4 pi over 3, we see that the enclosed charge actually is just a fraction of the entire charge residing on the sphere, and that fraction is determined by the ratio of little r cubed over the big R cubed. Now with that expression, we can go back to Gauss's law and see that the electric field must be equal to 1 over 4 pi epsilon naught, q enclosed over r squared. And now we're going to replace the q enclosed with our expression, cancel r squared in the numerator and denominator here of our fraction, and get for the final result q over 4 pi epsilon naught, the big radius, the radius of the charged sphere cubed times little r. Please note that this result shows that the electric field inside the charged sphere actually increases as we move away from the center of it linearly as a function of the distance. So with that, we have the two results. One is for the electric field outside that charged sphere, and the second result is how the electric field changes inside the sphere.